For now, acids ionize in aqueous solution to form a hydrogen ion. Sometimes we refer to acids as proton donors. Monoprotic acids have one proton to donate. Notice that this H plus is simply a different way of representing a proton. If we had an H, that is a hydrogen atom, we all know that a hydrogen atom consists of one proton that is being orbited by one electron. If we take that electron away, we now have no longer H, but we have H plus. And that H plus, isn't it, is simply a proton. So, an H plus is a proton. Diprotic acids, of course, have two protons that might be able to be donated. For example, sulfuric acid. And here's the equation showing the first ionization, that is, losing the first hydrogen ion, and the other product in that case is called the bisulfate ion, HSO4-. Now it turns out that the bisulfate ion could potentially lose a second H, that is, this one here, and that would be shown with this equation. It turns out, however, that only the first ionization occurs 100%. A rather tiny fraction of, see my laser pointer here with this equation, only a tiny fraction of these H's actually pop off. So, in a sulfuric acid solution, what we have in there, besides water, is quite a bit of bisulfate ion, quite a bit of H+, and comparatively tiny amounts of free sulfate ions. And with weak acids, of course sulfuric is a strong acid, with weak acids, the first ionization isn't even close to complete. Whenever you have a weak acid, of those H's, a very, very tiny fraction will pop off, we might say, and ionize. For now, bases are substances that accept hydrogen ions, that is, they accept protons. Hydroxide ion is very basic. It is quite happy to accept protons. When it does, we get water molecules. The most common weak base is ammonia, which has this formula, NH3. I recommend you memorize that. And it ionizes only about 1%. The equation for that is going to go something like this. The ammonia is going to react with water, and you can see that it has accepted a proton and has now changed into the ammonium ion, and then the other product is the hydroxide ion. You can see that it's a base because it has accepted a proton. We also have some hydroxide ion in the solution that we didn't have before, so certainly this will be a basic solution. A neutralization reaction has this form. Acid plus base yields salt plus water. And recall that the term salt means an ionic compound, that is, something with cations and anions. Let's try an example. Let's write the balanced molecular equation when nitric acid reacts with barium hydroxide. When we say molecular equation, we're distinguishing that from an ionic equation. In an ionic equation, we show all of the ions and represent what they're doing. In a molecular equation, we simply write all of the substances as neutrals. So that's what we're doing here. That's the formula for nitric acid. There's the formula for barium hydroxide. Acid plus base yields salt plus water. The salt is going to be barium nitrate, and then we're going to have water. Now we're going to need to balance this. We've got two nitrates on the right side, so clearly we need to have two nitrates on the left. Furthermore, we have two hydroxides on the left, and if we have two hydroxides with two H's, we're going to get, way over here on the right, two waters. Now let's write the net ionic equation of this reaction, and I'll write this kind of small so that we can see what we have here. Nitric acid is a strong acid, which means it ionizes 100%. So these ions here, hydrogen ion and nitrate ion, those are the ions that are actually present in the solution at first. Similarly, we're going to consider barium hydroxide to be a strong base, which means it will contribute barium ions and hydroxide ions. Since barium nitrate is soluble, Sol, Chuck, Kualke, no exceptions, that is a soluble compound. We have those ions floating around, and then we have water molecules that are neutral, that consist of bonded, you might say, OH and H ions. Are any of these ions spectators? I'm seeing here that on the left I've got free nitrate ions, and on the right I've got free nitrate ions. That looks like a spectator to me. I've got on the left free barium ions, and on the right free barium ions. That looks like a spectator to me. The net ionic equation is going to look like that. Let's write the balanced molecular equation when perchloric acid reacts with potassium hydroxide. Again, whenever we say molecular equation, we mean write the compounds as neutrals. There's the formula for perchloric acid. We should have had that memorized. And potassium hydroxide is KOH. The potassium cation is going to pair up with the perchlorate ion. Acid plus base yields salt plus water. All the coefficients are 1. What's the net ionic equation? Perchloric acid is a strong acid, so it's 100% ions. KOH is a strong base, so it's 100% ions. Potassium perchlorate, remember that Sol, Chukku, Alke, alkali metal, anything with an alkali metal is always soluble, so that exists as ions. And then again we have neutral water molecules. It looks to me like the perchlorate ions and the potassium ions, again, are spectators. This leads us to a reaction pattern. For every strong acid, strong base reaction, which is what we've had in this example and on the previous slide, strong acid, strong base, the net ionic equation is always that. So, if you have a problem and it says, write the net ionic equation for this strong acid reacting with this strong base, that thing at the bottom of the page, that's your answer. Final thoughts on acids, bases, and neutralization. 1. For now, acids are proton, i.e. H+ donors. Bases are proton acceptors. The most common weak base is ammonia, NH3. 2. A neutralization reaction between an acid and base has the following general form. Acid plus base yields salt plus water. 3. A molecular equation shows all substances in a chemical reaction as neutrals. We also reviewed in this lesson the net ionic equation, which shows only the species that participate in a chemical change.